Today's video is talking about what are called resonance structures. When we were drawing Lewis electron dot diagrams, one of the things that we had to do sometimes is we had to move two electrons in to make a double bond somewhere. For example, on CO3 2-, you get to this point right here where you're out of electrons, but the central atom doesn't have 8. At which point I tell you to just choose 2 electrons from anywhere. I'll take them from the top oxygen and you make a double bond there. But I just as easily could have made the double bond here, or I could have made the double bond there. Okay? And that's what a resonance structure is. A resonance structure occurs when a molecule can be drawn with a double bond in different spots but still obey the octet rule. Okay? So, if the Lewis electron dot diagram involves double or triple bonds, and there's multiple ways to draw that still obey the octet rule, then you have what's called a resonance structure. Okay, just like the one on the right there, the carbonate ion, CO3 2-, does have 3 different resonance structures. Again, one with the double bond up here, one with the double bond down here, and the one over here on the right. Okay, which of those 3 is correct? Really, none of them, yet all of them. Whoa. Okay? Because if they ask you to draw CO3 2- on a test, you're going to draw it just like this here, or with the double bond here, or with the double bond here, not in all 3 places at once. But you're going to draw one of those 3 with a double bond in one of those 3 places. Okay? But what it really is it's really a combination of those 3. Okay, the 3 different ways you can draw a resonance structure shows that there's 3 correct ways to draw it, but it's really not any of those 3. What it really is, and again, you would never ever draw it like this, but really what it is there's those single bonds here, and it's almost like there's a third of a bond in each spot. And all together, and again, never, ever, ever draw it that way. Always draw it with a double bond in one spot. But what they find is that the bond lengths in CO3 2- are all the same. Okay? With resonance structures, the bond lengths are equal between the 3 different or 2 different bonds. Okay? Like in ozone. Okay? Ozone has a double bond on the right, in this case, and a single bond on the left. And obviously, I could draw it with the double bond on the left and with them on the right, okay? And which one's correct? They both are, when really neither one of them are, because really what ozone is, it's like there's a bond and a half in both spots, which again, doesn't even make sense yet, but that's really what resonance is. That's the real structure of ozone, okay? So, let's look at an example of this, okay? HCO3-. Okay, and they're trying to explain to you how to draw it. It has 3 carbon to oxygen bonds. So carbon to oxygen, it has 3 of them. Okay? 2 of the carbon to oxygen bonds have the same length, and the 3rd carbon to oxygen bond is longer than the other 2. And then the hydrogen atom is bonded to one of the oxygens. So it doesn't matter which one, we're just going to bond that one in there. Okay, draw a Lewis electron dot diagram or diagrams for HCO3 that's consistent with that. Now, so let's back up here. Let's finish this. So we've got 1 plus 4 plus 18 plus 1. So that's 24 electrons all total. Let's put our dots here on our oxygens. And we need 4 on this one. Now let's look at our carbon. How many have we used? We've used 8, 8, and 8. So we've used all 24. We're out of electrons. Okay, in order to make this correct, we're going to take 2 electrons from one of the outer atoms and we're going to make a double bond. Okay, the problem here is that they say 2 of the carbon to oxygen bonds have the same length. Well, it's got to be these 2 right here, right? But one of them's a double bond, one of them's a single bond. That's the way you drew it, but that is not correct. What is it really? It's a resonance structure where you could have the double bond down here or the double bond up here. And yes, when you have that bond and a half in both places, then of course those bonds are the same length. Okay, when this question, this is an old test question, when this one was on the test, really threw my students for a loop because they're like, no, because it said they had the same length, but one was a double bond, one's a single bond. Anytime you can move that double bond around, we know that we can take that double bond, put those 2 dots back, get rid of 2 electrons here, and make a double bond there, and it's still a valid Lewis electron dot diagram. So therefore, there are 2 different resonance structures. And you didn't have to draw them both, but one with the double bond up here, and another one with the double bond over there, where yes, absolutely, those bond lengths are the same. Okay? And then the third carbon-oxygen bond is longer. Now, why is this carbon-oxygen bond longer? Because single bonds are longer than double bonds, and double bonds are longer than triple bonds. Triple bonds are the shortest. So why is this bond here longer than the other 2? Because these aren't, this and this are not single bonds. It's like they're bond and a halves in both spots. Okay? So that's why this bond here is longer than the other 2, because that's a single bond and the other bonds are like bonds and a halves, which again, what's going to be longer, a single bond or a bond and a half that's, closer to being a double bond? Of course, it has to be the single bond is going to be longer. Okay? All right, so example 2. The element Vb forms ions with the formula VbO32-. The following Lewis diagrams represent the ion. Okay, so we can see here that they have drawn 3 different resonance structures for this. And a lot of times what you'll see that double arrow between them to represent the different resonance structures. Okay, a student claims that VbO32- contains 2 VBO bonds of equal length and 1 VBO bond that is shorter than the other 2. Do you agree or disagree? Absolutely, you better disagree with that. Okay, and we disagree with that because when you have resonance structures, it's not a double bond and 2 single bonds. In regular chemistry, I think I talk about how it's like you have green paint and blue paint. Those are the 2 resonance structures. Okay, but what do you actually have? Oops, I said that backwards, dang it. It's like you have yellow paint and blue paint. What does the real molecule look like? It looks like, combine those together, green paint. Okay, so there is no real correct way to draw this VbO32-, and that's why we use resonance structures. But the actual arrangement of electrons in VbO3- is a mixture or a blend or a combination of those 3 resonance structures. So all of the bond lengths would be equal in length. Okay, so it's not this, it's not this, it's not this. It's all 3 of those put together to make the actual correct molecule, which again, with the tools we have, we do not have the ability to actually draw that molecule with the correct bonding as we can see it here when we're drawing Lewis electron dot diagrams. Okay? So absolutely, yes, disagree with that answer because, again, the real molecule is a mixture or a blend of all 3 of those.